Hello, this is Professor White. Today we will talk about geometric series. This is in the series of series and sequences for college algebra level. So make sure that you watch the arithmetic sequences series and then geometric sequences before you watch this video. In this one, I will talk about series notation one more time. Finite and infinite series, finding the nth sum, converting repeating decimals, which is kind of a really neat application of the geometric series. So let's get started. Alright, now if you watch the arithmetic version of that, so you kind of know the difference between a sequence and a series. For example, a geometric sequence will look something like this. Let's say I have a 3 and I multiply by 2, and then I multiply by 2, multiply by 2. Okay, that would be a sequence. A geometric, and this is finite. And a finite geometric series will be, it's going to be 3 plus 6 plus 12 plus 24. And we show them, since there are 4 terms, you can show S4. It's simply like this. You can go from 1 to 4. And what is the first term? 3. What am I doing each time? I'm multiplying by 2, I minus 1. Let's see if that works. 2 to the 0th power is 3. Second one, 2 times 3, yeah, it does work. So this one is called the sum notation, alright, summation notation. And here's a geometric series, and this is finite. So what's the difference between a finite and infinite? That means it goes forever. So I may have a geometric sequence that's infinite. If that sequence was infinite, it would have looked like this: 3, 6, 12, and then people would go dot, 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 okay? And then a geometric infinite one would look something like that. Geometric series that are infinite, it would be 3 plus 6 plus 12 plus 24, and they would go plus dot, 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 okay? And then how do they show that with the summation notation? S infinity, and it goes from I1 to infinity. That's going to be 3 times 2 to the I minus 1. Alright, now let's kind of play with this a little bit. Remember how an is for a geometric sequence. It's simply a times r n minus 1. Okay, let's go and write for n. If I'm adding just n terms, it would be a plus a times r plus a times r squared, all the way to a times r n minus 1. So I'm going to write it one more time. Sn a plus ar plus ar squared, blah, 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 ar n minus 1. Well, what I'm going to do, I'm going to multiply this with a negative r. When you multiply with negative r, you're going to have to introduce this. You're going to be, this is going to change to that, change to that. And the last one is going to change to ARN. Okay, now let's go add these two. When you add them, what you're going to get, SN, 1 minus R. But something interesting is going to happen. Look at these. These guys are going to go and cancel out. And you're going to end up with the first term and the last term. Oops, sorry, negative. And then factor that out. And let's write this nice and neat. Sn is going to be a 1 minus r to the nth divided by 1 minus r. Now let's look at what happens if instead of stopping at n, it kept going. Now let's say I want to find out what this is when my r is less than 1. What will happen to it? You're multiplying by n. Imagine n being huge. So when you take, let's say, 0.1 and you're multiplying a million times, you're getting something really, really small. What will happen is, when this happens, this term is going to drop out. Then your infinity simply is going to be a over 1 minus r. That is a very handy tool because I'm going to use this. Okay? So let's start with the finite sums and then infinite sums. So let's look at a finite sum problem. Let's say my a is 1, which is the first term. My r is 2. And S5 is going to be what? The first term, 1 minus r to the fifth power divided by 1 minus r. So what do you get? You're going to get a negative, and you're going to get 1 minus 32, which happens to be 31. So I don't have to go and add the first 5 terms. I just have to go and plug into the formula. All right. So a finite series is going to be shown like this, S finite, and it will simply go from I1 to n, a, r, I minus 1. An infinite series, on the other hand, is going to go 1 to infinity, a, r, I minus 1. Okay? And I know that for the infinite series, this is going to equal a over 1 minus r when absolute value of r, it doesn't matter, r is positive, negative, is less than 1. Okay, very good. So can I go and do a sum, infinite sum of a series that I am given? So let's look at that. Let's say I have 1 plus 1/3 plus 1/9, dot, 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 dot. And I'm looking for infinite sum. So what is that going to be? A over 1 minus r, because my r, I'm multiplying by 1/3 each time, and that's less than 1. So my first term is 1. 1 minus 1/3. That gives me 3/2 and 1/2. I didn't have to go and add million terms. It just gave it to me because this r is less than 1. So it's a very handy tool to do that. Okay, so all that is exciting, and but the most exciting application of this is converting repeating decimals, and kind of recognize that repeating decimals is actually a geometric series. So let's look at that example. Let's say I'm writing 0.3333. Okay? I want you to recognize that this goes forever. This is the same as taking the 0.3 and then dividing it by 1/10 and add that to it. Dividing it by 1/100 and add that to it, and so forth. Do you see that? So how does that work? I am actually multiplying by 1/10 each time. Okay? And my first term is simply 0.3. And actually, this thing is going to be then S infinity, which is a over 1 minus r. What is my a? 0.3. What's my r? 1/10. And this actually turns out to be, when you do the math, 1/3. And I know from arithmetic that 1/3 is 0.33333. So you can see all these things are connected. Well, let's go and do something maybe more exciting. Let's say I have 8254545. Actually, that was given to my daughter when she was in 6th grade. She didn't know anything about series or anything, but she was in a gate class, so they thought it was a good idea to really spin the kids' heads and then give them this problem and say, okay, can you convert this decimal into a fraction? And she was in tears. But you can do this easily because you know your series. Okay, so let's write this. So which part is repeating? This part, right? So 8.2 is your thing that you're going to add to, but how much are you adding? 0.054, right? So because that will be taken out by the 2, and this will be taken out by 8, right? 54. And then the next one is going to be 0.00054, and so forth. So you can write this as 8.2 plus, let's change this, 54 times 10 to the negative 3 plus 54 times 10 to the negative 5, and so forth. Okay? And let's look at this. What does this mean? Let's try to write this. 8.2 is simply 82 over 10. And and how is this going to go? This one is negative 3. And what are you doing each time? You're actually multiplying it by 1 over 10 to the second power. So your R is 10 to the negative 2. Does that make sense? So, and then what is my first term then? My first term is this guy. And this is my second term. So it's going to be first term, which is this guy, divided by 1 minus R. What's my R? 10 to the negative 2. And let's work this out. You have 82 over 10 plus, and let's clean this up a little bit, 54. And this is, yeah, you write this as 1 over 100, and you'll see how this works. That's going to be 1,000 minus 10. And what do you have? You have 82 over 10 plus 54 over 1,000 minus 10 is 990. Oh, guess what? I already switched. Okay, let me put this up because you're not seeing anything. I already switched to the fraction notation. So put it in the same denominator. You're going to get 8118 divided by 990, because that's your common denominator, plus 54. Okay, and that will give me 8,172 over 990. And you simplify that, 454 divided by 55. Without knowing any kind of algebra, it's kind of hard for an 11-year-old kid to figure this out. But after a couple of hours, she was able to do it in tears. Okay, so your decimal, and this may also come up like in 6th or 7th grade in GIG classes. They may say, well, is this thing a rational number? Because a rational number is a ratio of integers, and those poor kids needed to show that this is an integer and that's an integer, and you are doing a ratio of integers. But it is so much easier when you know algebra, so you can plug all that in all at once.